As we continue in our study of multivariable calculus, we're going to once again remind you that even though we're mostly working with just 2 independent variables, most of the ideas that we develop can easily be extended to 3 or more independent variables. When we took derivatives of vector-valued functions, we were taking the limit of a function of a single independent variable. Because it was a function of a single variable, we didn't really need any new calculus ideas because it still came down to the same derivative formula. So although we have been working in multiple dimensions, we have not done anything new with the derivative. But now we want to look at derivatives of functions of 2 independent variables. While the core concepts are going to be similar, we're going to need to expand our definitions. The first definition we'll expand is our concept of a limit. Definition. Given a function f of the independent variables x and y, we say that f has a limit L as xy approaches ab, provided that we can make f of xy as close to L as we like by taking xy sufficiently close but not equal to the point ab. And this is the notation that we use. Since you've already taken single variable calculus, these ideas should be familiar. You may have even encountered the formal epsilon delta definition of a limit in your previous calculus courses. You can use the same formulation for this, but the book sweeps that notation under the rug, and we will as well. The idea of being close but not equal to should remind you of graphs with removable singularities, where the function looks like it's headed towards one value, but when you get there, the value is something else. Remember that this function still has a limit because we're looking at points that are close to but not equal to the destination. When the limit and the value match up, we say the function is continuous, and that's something we'll loop back to shortly. In single variable calculus, there are only 2 sides that you can approach the limit from. You're either approaching from above or below. But for a function of 2 variables, you can approach the limit from all sorts of directions. Furthermore, you don't even have to approach from a straight line. The limit must be the same every single way that you want to approach the point. The power of the limit concept is that it is so stringent. This makes it somewhat easy for us to show that limits do not exist. All we need to do is identify 2 paths towards the same point that evaluate to different limits. In practice, you would need to write down some sort of function that defines a path towards the limit and then substitute. Activity 10.1.2 uses the function f of xy equals x over the square root of x squared plus y squared, and asks you to consider the limit at 0, 0 using straight lines of the form y equals mx. The key fact is that for this function, as x goes to 0, so does y. This means that you can make the substitution and calculate the limit along that line. In this calculation, the final result ends up not being a constant, but a value that depends on the slope that you picked. And this means that different ways of approaching 0, 0 can lead to different values, which means that the limit does not exist. Proving that a limit does exist turns out to be much more difficult. The problem is that you cannot use a path-based approach. There are infinitely many different paths you can take, and there's no single collection of formulas that accounts for them all. The book does an example of this that you should work through. Although the skills that are developed won't be used anywhere else in this course, the basic skills of working with inequalities and logic that are used really ought to be in your toolbox. The book lists 5 properties of limits, and while there's a lot of notation here, the ideas are simple and should be familiar. As long as the limits of our functions exist, then there are certain properties that they follow. The first one states that the limits of isolated variables are exactly what you think they should be. The second is that constants can be factored out of the limit. The third and fourth show that the limit respects addition, subtraction, and multiplication. The fifth one says the same with division, as long as you do not end up with division by 0. These results are important because it justifies all of the algebraic manipulations we're going to perform, but in practice, these end up being exactly the manipulations that you've been trained to do throughout your mathematical experiences, and so it's not that informative. The main consequence of these properties is that for the nice functions that we're working with, everything works out the way we expect they would. Earlier, we brought up the idea of continuity. A function f of a single variable is continuous at a if it satisfies 3 properties. F of a exists, the limit of f as x approaches a exists, and these 2 values are the same. Looking back at the removable singularity from earlier, we see that it isn't continuous because it fails at the 3rd property. The limit approaching x equals a is not the same value as the function at x equals a. Continuity for multivariable functions is defined in the same way. Definition. A function f is continuous at the point ab, provided that f is defined at ab, the limit of f as xy approaches ab exists, and the 2 values are the same. The book goes on to list a number of continuity properties, which are basically just reflections of the 4 limit properties from earlier. In short, continuous functions behave well with respect to addition, subtraction, multiplication, and division, as long as you're not dividing by 0. In our applications, the functions we're working with are basically all continuous. Our points of potential discontinuity are primarily from points that lead to division by 0. These technical conversations are important at higher levels of mathematics, but for this level it would be overkill. The functions that we're going to be working with are nice functions, and we don't have to worry too much about the pathologies.